Hello everyone. In the last session, we have studied head loss due to sudden expansion. So this derivation we have studied. You might have practiced this. The expression at the end is quite simple. V1 minus V2 whole squared by 2g is the head loss due to sudden expansion. Means there is a pipe of some diameter. The diameter has suddenly increased, not gradually. Because of that, there will be eddy formation. The velocity reduces. There will be a loss. That loss is given by V1, the velocity in the first pipe, V2, velocity in the second pipe, whole squared divided by 2g. That is the head loss. Now we'll see some numerical problems involving losses, maybe friction loss, maybe minor losses like sudden expansion or entry loss and then exit loss, etc. Let's see. Okay, here there is a problem. This is taken from earlier question papers. What it reads is water is supplied to inhabitants of college campus through a supply main. There is a pipe through which the supply is being done. The following data is given. The distance of the reservoir from the campus is 3000 meters. Means the length of the pipe involved is 3000 meters. So that's why I have written L is equal to 3000 meters. Okay, number of inhabitants are 400. So number of persons involved 400. Consumption of water per day of each of the inhabitants is 180 liters. So requirement of water is 180 liters per day per person it is. Then loss of head due to friction is 18 meters. They have given it. Coefficient of friction F equal to 0.007. Okay. If 1/2 of the daily supply is pumped in 8 hours, determine the size of the supply main. Okay. Now we'll work out what is the discharge required. The discharge required is total volume required divided by time. Then time they have said we have to pump it in 8 hours. So I have taken 8 hours. So 8 into 60 into 60, that gives you in seconds. Now what is the volume required? There are 4000 people. They require 180 liters per day. That is the requirement, right? Okay, here I think we should have done 50% of it, because they have said if 1/2 of the daily supply is pumped in 8 hours. So 4000 into 180 divided by 2 I should have done, and it is pumped in 8 hours. So 1/40 meter cube per second should be the rate of discharge. Or if I divide it by 2, actually I have missed that. I have taken full. So this should have been into half. Means it should have been 1/80 meter cube per second should have been the discharge. That's all. If you take half, I have missed that. Right, I have taken the full supply. 4000 into 180 divided by 2 I should have done, because half of the supply, and pumped in 8 hours. Okay. Then our usual equation, HF equal to 8FL squared, 8FLQ squared divided by G pi squared d raised to 5. You know the discharge. And then yeah, here I have done 1/40 into half I have done here. Then whole squared. Anyway, it is taken care of. That's fine, right? And then everything else is there. Only the unknown in the equation is diameter. So diameter comes out to be 0.108 meters. So to say 10.8 centimeters pipe is required. to bring the water. So if you look at the kind of question, it looks quite involved question or difficult or lengthy. But when you work out systematically, the total discharge required divided by time is the discharge. Total volume required divided by time is the discharge. And once discharge is known, you know the equation of head loss. So one of the unknowns is the diameter is found. So this is the kind of questions from question paper. Very interesting one. That's why I have taken June 2012. Okay. Okay. Here again the question is not given, but data is like this. The diameter D1 is 0.2 meters, the D2 is 0.4 meters, the discharge is Q equal to 0.25 meter cube per second. What is the head loss? Head loss due to sudden expansion. Very simple problem. Expression for head loss is given by, you know that it is HL is given by V1 minus V2 whole squared divided by G, right? That is what is the expression we have. Okay, that's good. Now Q is equal to A1 V1, A2 V2. We know the value of Q. Because of that we can work out velocity V1 as well as velocity V2, because A is pi d squared by 4 into V1, A2 is pi 0.4 squared by 2 because the diameters are given. V1 comes out to be 7.96, V2 comes out to be 1.99. Okay, now simple head loss equation is V1 minus V2 whole squared by 2G. Put two values in the expression, find out the head loss. Very straightforward question. There is nothing much to learn here. Just application of that formula. 1.816 meters is the head loss. There is one more question here. You can study here. There is a 4 meter water standing in a reservoir, and then it's a pipe running for a distance of 50 meters, right? And what is asked is, what is the discharge when the diameter of the pipe is given 0.2 meters? Consider minor losses. Consider minor losses. That's an important point here, because generally they say in many problems neglect, but here they have said consider minor losses. F is equal to 0.009 in HF equal to 4FLV squared. So they specify in some of the question paper whether it is 4FLV squared or FLV squared. In this they had mentioned in the question paper itself that HF equal to 4FLV squared by 2GD. In that 4 is, coefficient of friction F is 0.009. Okay. Now what are the head losses that come into picture? So when the water enters into the pipe, entry loss would be there. There will be friction all along, and then when it comes out, there will be exit loss at 0.2. So losses involved are loss at entry, friction loss, and loss at exit. So the total head loss when it comes out, it is coming at this level out. So total head loss would be 4 meters. Total head loss would be 4 meters. Now if I go on writing expression, entry loss is 0.5 V squared by 2Z. We know the expression, or we should remember them. plus friction loss is 4FL V squared by 2ZD plus exit loss is simply V squared by 2G, and all this should sum up to 4. Now if I take V squared by 2Z in this common and then work out for the other things, they come out to be 0.5 plus V squared by 2G is taken common. You have 4 into F into L by D. If you work out, I think it is 9. Here it is anyway 1. So if we simplify, you will be getting V as 2.73 meter per second. 2.734 meter per second. That is what is velocity. Now once you know the velocity, Q is equal to A into V. So that gives you the discharge. Discharge is coming to be 0.0859 meter cube per second, because it is after decimal, very small quantity. Because of that, at least around 4 digits is a must. Meter cube per second, and if you convert that into liters per second, you have to multiply by 1000. That's why it becomes 85.9 liters per second would be the discharge. Okay. So here there are minor losses as well as friction loss put together. They have asked a question. Okay. Here I have a problem. Water is flowing through horizontal pipe of diameter 200 mm, that is 0.2 meter, at a velocity of 3 meter per second. Okay, velocity is given. A circular solid plate of diameter 150 mm is placed in the pipe to obstruct the flow. Find the head loss due to obstruction in the pipe. If Cc, this is coefficient of contraction, something is cut equal to 0.62. So what is given here is, if we try to analyze, there is a pipe, flow is occurring, and there is one obstructing plate, so that you have water flowing only here, right? So earlier with a velocity of 3 meter per second, it is taking this area. If I call this as A1, right? A1 is the area with a diameter 200 mm. Now when there is a plate which is obstructing with 0.15 meters or 150 mm here, this area, if I say A2, this is obstructing, but what is available for flow would be A1 minus A2, right? A1 minus A2, because the flow is obstructed by a plate. So it is a case of sudden contraction, right? Suddenly the area is contracted, but contracted in slightly different manner. Not that the pipe is reduced in size, but there is an obstruction, something like that. Okay. Now what would be the flow velocity? Because A1 minus A2 would be the velocity, but there is a Cc. Now what is Cc? If you remember, coefficient of contraction is nothing but, right, actual area of the flow divided by I can say actual here and then effective there, effective area of the flow. That would be much better. So effective area of the flow divided by actual area of the flow would be Cc, right? So actual area of the flow would be A1 minus A2, Actual area of the flow would be A1 minus A2 multiplied by 0.62 gives you effective area through which the flow occurs, right? Now we'll see how I have solved it. Okay. I'll take out all these things. I can see it is December 2014-15 question paper, and it is a case of sudden contraction. The pipe diameter originally 0.2 meters, 200 mm. Flow is occurring with 3 meters per second. Okay, what would be the discharge here? Simple, Q equal to A into V, velocity is given. So pi d squared by 4 into 3, so that comes out to be 0.0942 meter cube per second. That is the discharge. Now, okay, here I have drawn the picture for you. The outside diameter is 0.2, inside obstruction is 0.15. This area, actual area through which the flow is occurring is A1 minus A2. That is to say pi d squared by 4 minus pi d squared by 4. That comes out to be opening area is 0.01374 meters square. Okay. Now CC, that is effective here. The term should have been effective rather than actual. Right here, effective area of the flow. Effective area of the flow divided by actual opening size, that is A1 minus A2, right? That is CC equal to 0.62. So effective area gets reduced. It is coming out to be 8.5188 into 10 raised to minus 3 meters square. Now the discharge Q has to be the same, right? So V2 would be V2 into effective area multiplied by Q. Is equal to area multiplied by velocity will be equal to discharge. So V2 comes out to be, because we know the discharge, now we know the effective area, so 11.06 meter cube per second would be the discharge, the velocity rate. Now how to calculate HL is simple. Sudden contraction, because it's a case of sudden contraction wherein the equation is 0.5 V2 squared by 2Z, right? So V2 as analyzed 11.06, so 0.5 into 11.06 square divided by 2Z gives you HL equal to 3.116 meters. Suppose in this problem the variation, I tell you, CC is not given. CC is not given. In that case, you could have simply gone like Q equal to A1 V1 first of all, and then you could have done this A1 minus A2 next area, A1 minus A2 multiplied by the velocity V2. You could have calculated straight away V2 like this, and then after getting V2 you could have used the same equation, but because they have mentioned about coefficient of contraction, we have to do all this analysis. Hope you have understood. If CC is not given, the thing is quite simple. You could have found the velocity V2 by this format. Once you know the velocity, you could have used this equation to find out head loss. Okay, fine. Next. Okay, slightly involved a couple of questions, earlier question papers, so that you will be well versed with the difficult questions also. So in this problem they have mentioned a sudden enlargement of water main from 240 mm to 480 mm diameter. The hydraulic gradient rises by 10 millimeter. Estimate the rate of flow. Okay. Now how to solve this? Hydraulic gradient rises by 0.01 meter, right, or 10 millimeter. Let's see how to go ahead. So this is a December 14, January 15 question paper itself, right? So here sudden enlargement, earlier diameter is 0.24, next it is becoming 0.48, right? Now here you can just see here P2 minus P1 by gamma, that is what is the rise or fall, right? P2, that is pressure at 2, is more because it is said the gradient rises, P2 is more, so P2 minus P1 by gamma, because it is given in head divided by gamma, is equal to 0.01 meters. This is given, P2 minus P1 is given. Now when P is given and obviously the velocities are involved, let us see how we have to go. Obviously by continuity equation, Q is equal to A1 V1 equal to A2 V2. This is usual. Because the diameters are given, I can find out the relation between V1 and V2, and it is V1 equal to 4V2. Fine. Now by Bernoulli's principle, because as I have told you, here there is pressure as well as flow velocities are involved, and assuming that it is a horizontal pipe, I can write total head at point 1 is equal to total head at point 2 plus the head loss. And this head loss I have written HF, but it is a head loss due to sudden enlargement. I'll correct it. So this is HF in the sense it is head loss due to sudden enlargement. The notation should have been HL. Anyway, P1 by gamma plus V1 squared by 2Z plus Z1, because it is horizontal, Z1, Z2 cancel off, P2 by gamma V2 squared by 2Z. But say Z1 is equal to Z2, go on, P1 minus P2 by gamma, this term, these terms I have taken on one side, plus V1 squared by 2Z minus V2 squared by 2Z equal to HL. Okay, from this expression HL is this, but what we know from sudden enlargement equation, that is head loss is V1 minus V2 whole squared by 2Z. This we know, this expression we have learned. So I am using that equation. By Bernoulli's equation I have got left part of the HL, and because I know the expression head loss due to, right, I have written in the earlier problem also, head loss due to sudden expansion is V1 minus V2 whole squared by 2G. That equation, that expression I have written on the right hand side. Okay, now in this I got V1 V2 and P1 minus P2 by gamma is given in this manner. So but P2 minus P1 by gamma equal to 0.01, so P1 minus P2 becomes minus 0.01. I have written minus 0.01. LCM is 2Z, 2Z gets multiplied by plus V1 squared minus V2 squared is equal to V1 minus V2 squared by 2G. So this 2G cancels off now here. Then further simplification. Okay, V1 squared minus V2 squared minus 0.1962 equal to this expanded V1 squared plus V2 squared minus 2V1 V2. So simplification gives this equation 2v2 squared. Okay, taking on the other side 2v2 squared minus 2v1 v2 plus 0.1962 equal to 0. Now I use this information here. So 2v2 minus 2 times v1 is 4v2 v2 equal to minus 0.1962. So v2 can be found to be 0.181. Hence Q is equal to A2 into V2. A2 is because of 0.48, so pi d squared by 4 into V2. So it comes out to be 0.0327 meter cube per second, or 32.7 liter per second is the discharge. Look at the way the problem is given, and it is a bit lengthy, but using all the information that we have studied or we should be knowing. So nothing wrong in asking these kind of problems also. So you should know how to handle this. It comes by practice, so please practice every day some problems. Okay, next one more of. Okay, here there is a problem. An oil of specific gravity 0.9, viscosity 0.06 is flowing through a pipe of diameter 200 mm at a rate of 60 liter per second. Find the head loss due to friction for 500 meter length of the pipe. Find the power required to maintain this flow. Slightly involved problem, but it covers all the concepts that we have learned right from the beginning. We'll see how it works. So this is from December 2014, January 15 question paper. Specific gravity is given, S is given, mu of the viscosity is given, it is in points. Diameter of the pipe is 0.2 meters. Q, the discharge is 60 liters, so to say 0.06 meter cube per second. Find the head loss, HF is how much. Friction, 500 meter length is there. Find the power required to pump. Okay, this is what is the problem. We'll see how we'll have to go. Okay, there are many things which are new to you. You can note down. So here I have drawn the diagram showing velocity distribution inside the circular pipe. So that is the discharge, velocity diagram. So at the periphery, the velocity is 0 because of viscosity. Hardly there will be any velocity. Velocity increases. You can just see here, right? Velocity increases. It will be maximum at the center. This is called V max, right? And then if you average it out, means if you assume that the velocity is here, I'll try to show, is perfectly uniform with the same velocity everywhere, then it is called average velocity. This is called average velocity. This is maximum velocity. Okay, there is a relation between V max and V average. V max is twice the average velocity. Okay, now because diameter is 0.2, from the center if you look at the distance at the periphery, it will be 0.1 meters. So y is equal to 0.1. Okay, now we'll go in a simple manner. Cross sectional area pi d squared by 4 I can calculate. Diameter is given. Discharge is given. Because of that I can calculate velocity, average velocity. Q is equal to A into V. So when I say Q is equal to A into V, obviously it is average velocity. So 0.06 is given, area I have calculated. So average velocity comes out to be 1.91 meter per second. But as I have told you, it is Vmax is equal to 2 times average velocity, it is 3.82. So that's what I have written, maximum velocity is 3.82 meter per second. So if you look at this velocity distribution, right, I can calculate what is the shear stress that is acting. If you remember viscosity problems, that is how it is. Okay, now this is the cylindrical area, pi dl, means all along the pipe which is having 500 meter length, right, diameter is 0.2, pi dl gives you the area of contact of water to the pipe. It is 314.16 meters square. Pi dl, you know how to calculate surface area of the cylinder. So surface area which is in contact with the water inside surface area, pi dl, right? Okay, next. Now as I have told you, tau, the shear stress is given by mu into V by y or du by dy. You remember that. Now mu I have substituted, it is in poise. You know that 10 poise is 1 Pascal second. Because of that I have divided by 10 so that it is in Pascal second. Pascal is Newton per meter square, second is there. So into this mu is substituted here, into this velocity which is maximum velocity 3.82 meter per second, divided by y, the distance is 0.1 meter, 0.1 meter. Now if you look at the units also, second cancels off, meter goes off, what you will be left with? Newton per meter square, which is shear stress. Yeah, it's fine then. So if you work out the values there, it is 0.2292 Newton per meter square is the shear stress. Okay, now shear stress is known. How much is the force, total force to push the liquid? Force is equal to the shear stress multiplied by cylindrical area, calculated cylindrical area. So this force which is required to be pushed against the friction is 72 newtons. Okay, now you want power. Power is what? The work done per unit time, right? Work done is Newton into meter. Work done, I will write it here. Force is Newton, I have calculated force, into distance gives you work done, divided by time gives you power, right? Work done per unit time is nothing but power, Newton meter per second. So force is there, and this term meter per second is nothing but velocity, and I know that average velocity is 1.91. so power required is equal to force into, you can just see there, distance divided by time or average velocity. So 72 multiplied by 1.91, that gives you equal to 137.52 Newton meter per second. So power will be equal to 137.52 joules per second, or it is simply watts. So this can be so many watts. Of course, lowercase letter w, it is watts. In abbreviated form, when you want to write, it is capital W. That is the power required, 137.52 watts. Now, what is the head lost? Because they have got, find the head loss due to friction. Okay, the power lost is given by actually formula like that. P is equal to gamma QH. This is the way how to calculate for power. This head can be anything, but in this case power lost, that's why head lost. Alright, how it comes, when you can check out here, gamma they are pumping water, so it will be 9.81 meter cube per second. I'll check only the units and then show you. So units are meter cube per second. I'm sorry, units are Newton per meter cube. Newton per meter cube into the discharge is meter cube per second multiplied by we got head in meters. So this meter cube goes, what you will be left with is Newton meter per second. So when it is Newton meter per second, it is obviously joules per second, or it is watts, right? So the same thing has happened here also, if you check, right? Now if you equate this 137.52 Newton per meter squared with the gamma, and then you have to substitute, because it is Newton meter per second, gamma has to be taken equal to not 9.81 but 9810 Newton per meter cube. This is how you have to substitute. And Q, anyway it is given 60 liter per second, so you have to put Q equal to 0.06 meter cube per second. So substituting HL, if you work out, HL will be 0.2336 meters. This is the head loss. So you can just see the problem is good problem, involved problem, which uses all the concept that you know right from the beginning, right? Power concept is there, viscosity concept is there. Like that, the problems can be there, or straightforward problems can also be there. So you have to practice and then be well versed with that. So with this, I think we'll stop. Thank you.